Okay, I know you don't have this handout, but I kind of looked at the notes that I had done, and I feel like you need a little extra practice with U substitution, that you're not going to see all the different forms that you might see on the AP unless we do a few more examples. So what I'm going to do in this set of notes, I'm going to go through and do what I would say are like classic types that you might see, and I'm going to leave all the U tries for you to do on your own, but I just want to do a couple more examples. All right, so also, when you're doing these, you don't always have to do the U substitution. I pretty much will always write down the U and the DU, but I don't always substitute it in if it's a fairly straightforward problem. It's only if it's a little complicated that I might go ahead and substitute it in. All right, so let's take a look at our first example here. So when you look at it, you have to identify the inner function. And so what we're looking at is it doesn't really matter what the inner function is, but we're seeing that the outer function is a power rule, that the f of g of x, the f part, is a power rule. So when I take a look at this part right here, I see that I have a power that has stuff inside of it. So I pretty much am going to say, okay, let's let u equal x squared plus 1. Then du equals 2x dx. I also start to shortcut just a little bit in that I don't put it in the derivative form. I immediately go to differential form because I know that's what I'm using here. Now, what we see very quickly is that we do have our derivatives of the stuff. Here was my stuff, that's my u, and then that was the derivative of the u. So, I mean, I could pack this back in. I could actually do the u substitution and be like, hey, it's going to be the integral of u to the 12th du. If that helps you see what antiderivative you're actually doing, please do that. Put it in. But you don't have to. We can go straight from here over to here and be like, hey, I have stuff to the 12th. The antiderivative of the stuff to the 12th is going to be stuff to the 13th divided by 13 plus c. And you kind of ignore this portion right here because that was the derivative of the stuff. So you can kind of think of, oh, I'm just going to pack that back up. That came from the derivative of the inside. So you can kind of ignore it when you go backwards as long as you have it. In the end, you do want to make sure that your final answer is in terms of x, not in terms of u, even if you write it down. All right. Now, I'm going to leave the u tries for you to do on your own. Those are all power functions on the outside. Let's take a look at when the power function is an exponential, or the outer function is an exponential. So again, taking a look at this and going to kind of what's the quote-unquote outside function, you kind of have to look at this a little bit. You see that I have that e there. The other part here, the exponent, remember the exponent is the input, the inside of an exponential function. And so I see that that inside has a function. I'm going to make that my u, 1 plus tangent of v. And then the derivative in differential form, du, the derivative of tangent is secant squared. And so we see, without me having to rearrange it, that this with the dv is going to actually be the du. Again, you can skip this step, or if it helps you see what's going on, go ahead and make your substitution. And then we say, okay, what is the antiderivative of e to the u? It would be e to the u plus c. And I have a tendency to go ahead and just plug back in at this point and do my plus c, saving myself a little bit of time. Right? I'm going to leave a, b, and c for you to do, where the outer function is exponential. Now, looking at these, I'm going to do one of these in these challenge problems for you. And that's just because I want to remind you that when we're looking at this, our outer function, okay, is going to be the base 3 exponential. Our inner function is going to be the input to that exponential. And you initially are going to look at this and be like, wait a minute, there is the derivative of the stuff on the outside, but if you've forgotten, you're going to think that there's some extra ln of 3 there. But if I let u equal 2x minus 3, du is going to be 2 dx. And those are the things that I've highlighted in yellow. But I want you to recall, so we'll do a recall up here, the derivative with respect to x of 3 to the u, just leave it as u, is going to be the natural log of 3 times 3 to the u. So just kind of remember that there was a rule constant that is supposed to be there when you do the derivative of a base 3 exponential. So this ln of 3 is there because it's part of the rule constant for the derivative of the natural log. So it is part of the derivative of the exponential, part of the derivative that's there. When I'm going to the antiderivative then, and I make my substitution, I'm going to leave the ln of 3 there, and then it's 3 to the u, and then the 2 dx becomes du. That's what you would expect in terms of your quote-unquote known derivative, so that when you do the antiderivative, it would be 3 to the u plus c, or 3 to the 2x minus 3 plus c. And as always in all of these, you can always check your answer by taking the derivative. Right? Let's look at another example here where your outer function is a trig derivative. And likewise, I'm leaving all the extra ones for you to try. So in this one, you look at it and it looks pretty complicated. There's a lot going on. We've got a log, we've got a sine, and so on. But what we're basically going to recognize, though, is that our outer function is going to be the sine of x. And then all the rest of the stuff that we're looking at, and so the inner function here is going to be ln of ax, where a is a constant. So if I let u equal the natural log of ax, okay, and then I go to take the derivative of that and put it in differential form. Remember, the derivative of the natural log, the stuff, is 1 over the stuff times the derivative of the stuff, and then, of course, times the dx because we have it in differential form. And this ends up being du equals 1 over x dx. So I'm going to go ahead and I'm going to rearrange this just a little bit to help us see what's going on here. So I really have sine of this natural log of ax, and then I have 1 over x dx. So when I rewrite it like that, I can see that I'm really taking the antiderivative of sine of u du. The what is sine the derivative of? Sine is almost the derivative of cosine. You're missing a negative. So I kind of will add in a corrector on here. So I add that corrector in. And so the antiderivative of negative sine u is going to be cosine of u plus c. And then that would be negative cosine of this ln of ax plus c. So we can do that. All right, I'm going to leave the u tries down here where the outer function is a trig derivative. And I'm just going to point out one thing to you here. Like when you're looking at this, the fact that you have a secant squared in b, that secant squared, remember, secant squared is a known derivative of something. And so that will help us out in terms of our inside-outside function when we're doing it. So try those. All right, let's take a look at example 4. All right, so now we're looking at a class of integrals where your quote-unquote outer function is really 1 over stuff. That the idea is that you're looking for a log derivative. And remember that when you have a log derivative, the derivative with respect to x of the log of u, where you have stuff, is 1 over the stuff times the derivative of the stuff. So we're looking for things of that form where you basically have the derivative in the numerator and what you took the derivative of in the denominator. So it's the 1 over stuff times the derivative of the stuff. And so when you look at this example that I have here, your strategy for a lot of these fractions is going to be to see if you can make u equal to the denominator. And that's where we're going for this log rule. And so when we talk about that, and I go, okay, what's the derivative of that denominator? The derivative of cosecant is negative cosecant cotangent. So a negative times a negative, because of the minus that's right there, would become cosecant x, cotangent x, dx in differential form. So while this looks really complicated, you're really integrating 1 over u, and then the whole top and this part right here is that part right there. That becomes your du. So the antiderivative of 1 over u du is the natural log absolute value of the u. I'm going to go ahead and put it back in, cosecant of x plus c. So that kind of shows you this 1 over stuff times the derivative of the stuff that you're going to be looking for your log rules. All right? Now, I do want you to be careful, though. You get in this idea of you see fractions, and you want to say that all of them are log rules, and they are not. Notice in this one that I would kind of consider the inside function under that radical. And so for this one, I would let u equal 4 minus 9w squared. I would not let it equal the whole denominator, because clearly what's in the top right here, the w right there, is not going to be the derivative of something with a square root. But the w is the derivative of just the 4 minus 9w squared. So du would be negative 18w, dw. And you see that we're missing a constant. So this is an example of where we're going to need a corrector. And so our corrector in this case, I need a negative 18 in there. So I'm going to put the corrector on the outside, and then I'm going to need a negative, and I'm going to put the negative 18w in on the numerator. And I'm going to rewrite this as 4 minus 9w squared to the 1/2 for a moment, dw. Because what this is going to end up being, and I'm going to go ahead and make sure I do the u substitution here, the negative 18 dw, that's going to become the du. And this u in the bottom to the 1/2 is really u to the negative 1/2. So this one was a power rule, not a log rule when we were looking at it. The antiderivative of u to the negative 1/2 would be u add 1 to the power, 1/2, divide by the power is the same as multiplying by 2, plus c. Then I'm just going to simplify negative 1 over 9 and put my square root back in and put my u back in, 4 minus 9w squared plus c. All right, now from there, I'm going to leave you to fill in these log rules, these inverse trig rules down here. So these don't even have chain rule. These are just the basics that you were supposed to remember, kind of working backwards from. So I'm going to let you write those down. But I'm going to come down here and be like, if these log rules that we're looking at, let's just do the first one together. The antiderivative of 1 over the square root of 1 minus x squared is the inverse sine of x plus c. Right? Now, of course, that's going to be way more complicated if there is a u substitution here. If there is actually a inside function like 2x or 4x squared or something like that, that becomes a more complicated problem. Now, I'll tell you that what we've learned is that really we're just going to memorize a different form of this. Instead of going through the whole u substitution for a lot of these, we're simply going to memorize a special form of antiderivatives that end up being inverse sine. Notice that right here, whatever your inside function is what's going to go there. Then we have a constant over here, and that constant is going to go there. So anytime you're looking at this problem, like for my example here, I'm going to say that my a, when I look at it, is going to be 2 because of the 4. And 9w squared is the square of 3w. So that's going to be what I'm going to put there. And then I'm going to go ahead and do my du would be 3 dw. We see that we are going to need a corrector. So if I put in a 3, I'm going to put a 1/3 out. And so this ends up being 1/3 antiderivative of, oh, I'm not even going to do that. Notice that I started to correct it and put it in, but, well, we do want to do that, but now we just need to, all right, so we just use the rule, we put in the u, we put in the a, and we bring our corrector with us. All right, try the ones at the bottom and